We've seen the cylinder head, we've discussed that. Now let's talk about the valves. And we already know that the gases flow through the cylinder head, entering through the intake ports on this side, exiting through the exhaust ports. And if we were to look at this on the engine, we would find that we have the intake manifold on this side and the air intake. And on this side, we would have the exhaust manifold and the exhaust going off towards the back of the car. And the job of controlling that flow of gases falls to the valves. So inside the ports, we just have a clear passage straight into the cylinder, into the combustion chamber here. And the valves act to close that passage and open it at the appropriate time. The minimum number of valves that we need on an engine is 2. We need 1 intake valve and 1 exhaust valve. And what you see here is we actually have 4 valves on each combustion chamber, 2 intake valves and 2 exhaust valves. So this is what's known as a multi-valve engine. And the reason engines these days are almost all multi-valve engines, either 4 valves, sometimes 5 valves per cylinder, is that you get a more efficient flow of gases in and out of the cylinder, which is what produces the power in the engine. So all the engineering in valves goes into ensuring that we have an efficient flow of gases into the cylinder and out of the cylinder. The way these valves fit into the cylinder head is like so. They just slide into a valve guide that runs through the cylinder head and out at the top. And there's 2 intake valves, so we pop those in there, and these open and close like this. So we should take a look at the valve assembly, how the valve actually works. And I'm going to make something to illustrate this because it's quite hard to see how the valve assembly works. We have a valve, we have a spring, we have a cap, but without a little bit of DIY engineering here, it's going to be hard to show how this works. So, time to do some woodworking. Let's look at these bits up close. So we have here the valve, and the valve is made up of the stem, which is the long shaft that fits through the valve guide, and the head, which is basically the part that seals the engine. And the face, the valve face, is this shiny part that you can see around the underside of the head, or the top side of the head as we look at it. And that face is what forms the seal. So inside the cylinder head here, we have a valve face, and that face mates up against the valve seat. So the seat is this shiny ring which is pressed into the head, and the face and the valve seat fit together and create a gas-tight seal. So the finish on this face and the finish on the seat need to finish. So when you hear people talk about grinding valves, what they're talking about is grinding the face and the seat together to form a perfectly mating surface. Valves themselves are made in 2 parts usually, and the stem will be made of a hardened steel, and then the head of a titanium or a carbon steel, something that can take serious heat from the combustion chamber. And those 2 parts are then welded together. So you'll see there's often just the trace of a weld, which is always ground to make it perfectly smooth, but you can just see the slight difference in materials here. So the fit between the face of the valve around the back side of the head and the valve seat, which is inside the cylinder head, is vital. It serves 2 main purposes. Firstly, it creates that gas-tight seal. So any gas that's escaping through this is going to cause a loss of compression, a loss of power. But also, the valves get extremely hot because they're dangling directly into the combustion chamber. So they take an enormous amount of heat. And the way that heat gets away from the valves, or is dissipated from the valves, is through this meeting between the face and the seat. So again, the finer the tolerance between those, the closer the fit, the more easily that heat can be dissipated. The valves are closed about 3/4 of their time, so only 1/4 of the time they're open. And the other 3/4, they should be resting on their seat, and that heat should be being carried away into the rest of the head. Now the seats on a cast aluminium head like this will be inserts. There'll be a steel insert which is pressed into the head. On a cast steel head, then the seats are often just machined directly into the head because that's a tougher material, so there's no need for a harder insert. This is an intake valve and this is an exhaust valve, and they are the same design, but the exhaust valve is smaller and is also made of a tougher material generally, because the exhaust valve really takes a lot of heat. The intake valve takes heat to its surface that faces into the combustion chamber, but the exhaust valve takes heat not only on this surface here, but also all the way down as the exhaust gases make their way into the port and all the way around the stem of the valve. So the exhaust valve needs to be tougher, it takes more force. The reason it's smaller is if we were to look at the holes on the cylinder head here, we can see that the intake ports, the intake holes, the intake valves are bigger than the exhaust valves. And that means that we have a bigger area for the intake gases to flow through into the cylinder. The reason is it's easier to blow things out than to suck things in. So if you imagine taking a straw, it's much harder to suck air through the straw than it is to blow air out of the straw. And that's exactly what's going on here. As we're drawing in air into the cylinder, it's being sucked in by the piston moving down. And that sucking is not as strong as the force of the piston coming up and forcing the exhaust gases out of the cylinder. So that's why intake valves are always bigger or more numerous, because in some engines you'll find there'd be 3 intake valves and 2 exhaust valves. And what we're interested in is this cross-sectional area through which gas can flow into and out of the cylinder. The valve stem fits into the valve guides, as we've talked about. So the valve guides are pressed into the cylinder head and they can wear and can be replaced, but they should have a tight fit against the valve stem. And there's also the valve seal, which stops any oil from making its way down along the valve guide and into the ports or even into the cylinders. So that's particularly important on the air intake side, where there is a sucking low pressure area which is going to pull the oil down the valve guide. So that's the side that has oil leaking in, whereas on the exhaust side we have pressure inside that port pushing out, and that's going to push up, and it's going to attempt to push exhaust gases into the cylinder head. So it's going to travel up from inside the port and along the stem of the valve into the cylinder head. Both situations we want to avoid, so that's the job of the valve seals. The valve spring is what holds the valve closed. So if we take a look at this spring, you can see that the coils of the spring are closer together at the bottom. So that's always the bottom side of the spring. Sometimes these springs are symmetrical, in which case it doesn't matter which way is up or down, but it's worth checking the manual to see which way a spring fits. And the spring not only holds the valve closed, but it also holds the valve against whatever's pushing it to open it. So for example, the camshaft on this engine, as the camshaft acts on the valve stem, it pushes it to open it, and the job of the spring is to hold the tip of the valve against what's pushing it, which in this case is actually a follower, but we can imagine it being the camshaft. And what we don't want is for the valve to open in contact with the camshaft, and then as the camshaft moves away and the valve should be closing, we want to maintain that contact. So as something pushes down and pulls up and pushes down, we want to keep that contact there. What we don't want to happen is for this sort of thing to occur, where the valve is losing contact with its pushing surface. That's a condition known as valve float, and you end up with valves which are remaining open for longer than you want them to, and essentially you've sort of lost some control over the valve timing. We're going to look at a lot more detail at camshafts shortly, as soon as we've bolted this onto the engine, but that's the role of the valve spring. The strength of the spring is specific, so there's a very exact strength that we want, a stiffness of these springs. If the spring's too strong or too stiff, then we're wasting energy pushing against it to open the valves, and these valves are opening, each valve, and there's 16 of them, are opening minimum 10 times a second, or an average of 10 times a second, and up to 30 times a second. So really, that's a lot of times that we're pushing against these springs, and we don't want to waste energy, because all the energy that goes into opening these valves comes out of the energy that's being used to drive the wheels. So we want as much energy going to the wheels and as little being wasted on pushing springs in the top of the engine. So too strong, that's not good. Too weak, and it won't close the valve fast enough at high speed. So as we just demonstrated, we need to keep the contact between the valve and in this case, the follower, in order to prevent valve float. So specific strength of springs, and that's one fine piece of engineering in an engine. What's left to talk about is faults with valves. What can go wrong with valves? There's two main faults that occur with valves. One is a burnt valve, and a burnt valve is essentially where some fault or some sort of weakness in the valve, maybe a crack on the edge of the face, has opened up, and the exhaust gases and the heat in the combustion chamber, but particularly the exhaust gases, have eaten away at the face of the valve, and that causes a crack or a small hole or something similar in the edge around the circumference of the valve head here. That creates an opening, or creates a poor seal between the face and the valve seat, so we've lost compression inside the cylinder in that situation. The other thing that can happen is a bent valve. So what happens inside the engine is the valves are constantly opening and closing, and they're in a dance with the piston, and as the piston's moving up and down, the valves are opening and closing at this correct time, and the timing between those, which we'll look at shortly, is very important, because if the piston comes up at the same time as the valve is open, then there could be contact between the top of the piston, the crown of the piston, and the head of the valve, and that contact, just one piece of contact there with an incredibly high speed piston, would bend the valve. It bends the stem of the valve, or it just bends the head here. There's two different types of engine. There's an interference engine. So an interference engine is one where the valves and the piston use the same space at some point in the cycle, and the timing ensures that when the valve is open, the piston is down, and when the piston is up, the valve is closed. That's an interference engine, and in an interference engine, there can be contact between the head of the valve and the piston because they overlap, their strokes overlap. A non-interference engine is one where there's no possibility of the valve contacting the top of the piston because they don't overlap and they don't at any point occupy the same space, even if the timing was completely out. So there's a difference. Interference engines can have contact between valves and pistons and cause a bent valve, and non-interference engines, that can't happen. It's not possible to repair valves, so if a valve is bent or you've got a burnt face, that valve goes in the bin, you need a new one. Okay, we've talked about everything on a valve assembly. We'll now install the valves into the cylinder head, and then we can bolt the head onto the block and continue with the camshafts.